Cigarettes on cigarettes, my mama think I stink. I got burn holes in my hoodies, all my homies think it stink. I miss my cocoa butter kisses.
Now we're going over LHopitals Rule. So I'll just write it because it's kind of cool to write. LHopitals Rule. Okay, so basically this comes into play when you have a limit. So as x goes to a is some number, of f of x, some function of x over another function of x. Okay? So what L'Hopital says is that when this, the f of x over g of x, has an indeterminate form, so indeterminate forms include anything such as the following: 0 over 0, infinity over infinity, 0 over infinity, the other way around, 0 times infinity, and etc. Basically, whenever you have zeros and infinities, some kind of combination of them, then it's indeterminate. That's what it's considered. So anyways, L'Hopital says that whenever this happens, when your limit's going from x to a, when your x is approaching a, and f of x over g of x is some form of this, then the following equation holds true. So this is your limit. That's what you're given to evaluate. Then you could do this. Limit as x goes to a of f prime of x, that's an f, over g prime of x. So basically you just take the derivative, the first derivative of the top, and then you put it over the first derivative of the bottom. And then you evaluate the limit from there and see how it turns out. And sometimes the case happens where even after doing this once, you'll still get 0 over 0 or some other indeterminate form, and then you just apply the rule again until you actually get a determinate form. So let's try an example. Let's try this one. Okay. So this is in your book as well, if you would like to reference that after this and look back at it, but I just wanted to do it in real time so you could see how it could be solved. Alright, so let's try evaluating this right off the start. So if we plug in 0, we get e to the 0 minus 1 over cosine of 0 minus 1. So this equals e to the 0 is 1, and then the minus 0 and minus 1. And then we have cosine 0 equals 1 minus 1. So as you can see, we get 0 over 0. So we have to use L'Hopital's, which says we're going to take the derivative of the top and then put it over the derivative of the bottom. So the derivative of the top is going to be e to the x, and that's just itself, right? And then minus, first derivative would be 1 here, and this negative 1 just becomes a 0. Okay, and that is put over a negative sine x, right? So let's try it now. Now we have e to the 0 minus 1 over negative sine of 0, and this equals 1 minus 1 over, that is 0 as well. So we get 0 over 0 again. Alright, let's try it again. Limit x goes to 0. So now we take the derivative of this one. So derivative of e to the x minus 1 is just going to be e to the x. And derivative of the bottom is just negative cosine x. Alright, let's try it one more time. E to the 0 over negative cosine of 0 equals a positive 1 over a negative 1. Okay, so our final answer is going to be negative 1. See how it takes, this time it took us twice. We applied the rule twice in order to get a determinate answer. Okay, now here's another application of it when you are comparing growth of graphs. So comparing growth. Alright, so let's say you have your limit, so x, this time instead of going to a, it'll go to infinity. So basically, as the graph keeps moving to the right, what happens in the long run? So we're going to be comparing f of x to g of x. And the way you do this is that if, let's see. So if this limit, and if you do need to apply L'Hopital's, you can. Oh, that's another thing I was going to mention, is x doesn't have to always approach a, like a fixed number. Even if it approaches infinity or negative infinity, and you get some indeterminate form, then you could still apply L'Hopital's rule. Okay, so this is true as well, as far as, like I said, when x approaches infinity or negative infinity, or just a constant like a. Okay, so when your result equals, it can equal one of two things, or, yeah. So when you're comparing growth anyways, if it equals infinity, then this means that f of x, or f prime of x, same thing. So when f of x, so your f of x on top is growing faster than the bottom, okay, which is your g of x. So this means f of x is faster, and g of x is your slower. The second, so this is the first option that could occur, and when you have a second option, this is when it equals 0. So on the other hand, then that means that your g of x is growing faster in the long run than your f of x. Okay, and the way that they write this, so 0 is when g of x is faster. Okay, alright, so let's see. Another way to write this, let me see. So I'll write it over here so you can see it better. So when your result is infinity, then that means that f of x is bigger, or it's growing faster, that's what this symbol means, than your g of x. Okay, and exactly the opposite for 0. Then g of x is growing faster than f of x. Okay? Alright, now for a last point. So a special case is when x to the n, so n is any exponent, is always going to grow slower than e to the x. No matter if you have n equals 1,000 or something, it's still going to grow slower in the long run than e to the x. Because, let's see, the graph is going to look something like that. Okay, so the first graph that I drew, that's your x to the n, so the right one here. And then this is your e to the x. So eventually it will overtake your x to the n. So limit, in limit terms, this is e to the x over xn is always going to be infinity, because the top is always going to grow faster than the bottom. Okay? So that just wraps it up, and I hope you watch the homework video.
Cigarettes on cigarettes, my mama think I stink. I got burn holes in my hoodies, all my homies think it's thick. I miss my cocoa butter.